S1. Your phone buzzes. GPS acting weird. You check the signal 3 bars should be fine, but your map app keeps jumping, placing you 2 blocks away from where you actually are. Outside, pilots flying over the Arctic notice their radios crackling with static. And 250 miles above, astronauts on the International Space Station glance at radiation monitors that just ticked upward. Something invisible just arrived from 93 million miles away. Proton flux reaches 10 particles per square centimeter per second per steradian. That number means nothing to you, and that's fine. What it means practically is this. Satellites start getting confused. An S1 storm is what happens when the sun burps. A small solar flare releases energetic protons that take anywhere from 15 minutes to several hours to reach Earth, traveling along the sun's magnetic field lines like cars on a highway. When they arrive, they hit our satellites first, the International Space Station, GPS constellations, communication satellites sitting in high orbits. The effects are subtle. GPS might be off by a few meters instead of a few centimeters. Not enough to make you miss your exit, but enough to throw off precision agriculture systems or surveying equipment. Radio communication across polar regions degrades slightly because the protons slam into the ionosphere, disturbing the very layer of atmosphere we bounce radio signals off. For astronauts, S1 storms mean elevated radiation exposure. Nothing immediately dangerous, but enough that mission control starts monitoring. It's like getting an extra dental X-ray. One won't hurt you, 100 might. The physics behind this is fascinating. When energetic protons hit the upper atmosphere, they collide with oxygen and nitrogen molecules, ionizing them and creating a cascade of secondary particles. This ionization disrupts the smooth layers of the ionosphere that radio operators depend on for long-distance communication. Think of the ionosphere as a mirror made of electrified gas, hovering 50 to 600 miles above your head. Radio waves bounce off this mirror, allowing communication across vast distances without satellites. But when protons slam into it, the mirror becomes warped and unstable. Some radio frequencies pass straight through where they should reflect. Others scatter in random directions. These storms happen constantly. Right now, as you read this, there's a good chance an S1 storm is in progress somewhere between the Sun and Earth. Space weather monitoring stations track them like meteorologists track rain clouds. The difference? You can't see these storms coming with your eyes. You need instruments sensitive enough to detect individual charged particles racing through the void. The Sun throws S1 storms at us about 50 times per solar cycle, which lasts 11 years. We've learned to live with them the same way we live with rain. Satellite operators factor them into their mission planning. Airlines adjust flight paths. Astronauts check the forecast before scheduling spacewalks. Ground-level effects are minimal. Most people go about their day completely unaware that a radiation storm is happening. Your phone works fine. Your car's GPS might take an extra second to lock onto a signal. The invisible particles sleeting through Earth's upper atmosphere might as well not exist for all the impact they have on your daily life. But every now and then, the proton count doesn't drop. It climbs. And when it reaches 10 times higher, satellites stop being confused and start bleeding. S2. Proton flux, 100 particles per square centimeter per second per steradian. 10 times worse than S1. And that factor of 10 makes all the difference. S2 storms hit us about 25 times per solar cycle. The energetic protons start causing what's called single-event upsets in satellite electronics, bits of memory flipping from 1 to 0 or vice versa because a proton smashes into a transistor. For most satellites, this isn't catastrophic. They have error correction systems, redundancy, and radiation-hardened components. But consumer electronics in space, CubeSats, commercial communication satellites with cheaper components, they start throwing errors. A satellite might reboot itself unexpectedly. A camera might capture corrupted images, pixels rendered as static. GPS accuracy degrades noticeably, sometimes off by tens of meters. Aviation feels this one. Planes flying polar routes which fly higher and closer to where Earth's magnetic field funnels radiation like a cosmic drain receive elevated doses. Airlines start rerouting flights away from the poles, adding time and fuel costs because exposing crew and passengers to high radiation becomes a real concern. The radiation dose at cruising altitude during an S2 storm can be several times higher than normal. For a single flight, this isn't dangerous. But pilots and flight attendants who fly these routes regularly start accumulating significant exposure. Airlines keep detailed records, tracking cumulative doses over careers, because there are regulatory limits that can't be exceeded. Here's what's happening inside those satellites when a proton strikes. Modern spacecraft use transistors measured in nanometers, so small that a single energetic proton can dump enough charge to flip a bit. Imagine a library where every book represents a piece of data. Now imagine someone randomly swapping pages between books. That's what's happening in satellite memory. Astronauts on the ISS retreat to more shielded areas of the station. EVAs, spacewalks, get postponed. You don't want to be outside in a spacesuit when a river of energetic protons is flowing past. The thin fabric and layers of a spacesuit offer almost no protection against high-energy particles. What shields you on the ground, the entire atmosphere, is absent in orbit. High-frequency radio communication across polar regions becomes unreliable. Military operations that depend on over-the-horizon communication start switching to backup systems. Scientific research stations in Antarctica have trouble calling home. Radio operators hear nothing but hiss and crackle where clear voices should be. As two storms typically last a day or two, the sun's tantrum passes, the proton flux drops, and systems recover. Engineers download telemetry from satellites, checking for damage, finding minor glitches that can be patched with software updates. It's a manageable problem. The technology holds. Contingency plans work as intended. We breathe easier. But what happens when the instruments show the proton count isn't stabilizing? When it keeps climbing and suddenly you're staring at numbers 10 times higher, where satellites don't just glitch, they start to die. S3. Proton flux. 1,000 particles per square centimeter per second per steradian. We're officially in dangerous territory now. S3 storms happen about 10 times per 11-year solar cycle. They're the kind of event where space agencies issue warnings, airlines scramble, and satellite operators hold their breath. The energetic protons are now numerous enough and energetic enough to cause serious damage. Satellites begin experiencing multiple single-event upsets, tiny errors that cascade into system-wide failure. Solar panels degrade faster as protons knock atoms out of their crystalline structure, reducing power generation efficiency permanently. Star trackers, the instrument satellites use to orient themselves, start seeing false stars, protons hitting their sensors, and creating phantom light sources. Satellites lose their sense of direction and tumble. When a satellite tumbles in orbit, it's not just embarrassing, it's catastrophic. Solar panels need to face the sun to generate power. Antennas need to point at Earth to communicate. A tumbling satellite is blind, deaf, and powerless. Ground controllers work frantically to regain control, firing thrusters to stop the rotation. But if the star trackers can't see real stars through the storm of false signals, stabilization becomes nearly impossible. The biological risk escalates dramatically. Astronauts are now confined to the most shielded modules of the ISS. Any EVA is absolutely forbidden. A spacewalking astronaut during an S3 storm would receive a radiation dose equivalent to several CT scans per hour. Mission Control watches radiation monitors obsessively, calculating accumulated doses because astronauts have career limits. Too much radiation and you're grounded for life. The radiation isn't just dangerous, it's insidious. Unlike a sudden blast of radiation from a nuclear event, solar radiation storms deliver a sustained dose over hours or days. The body's repair mechanisms can handle some damage, but when protons keep hitting cells, breaking DNA strands, creating free radicals, the damage accumulates faster than it can be repaired. This is when long-term health effects become inevitable. Every cell in your body contains mechanisms to repair radiation damage. Enzymes detect broken DNA strands and attempt to reconnect them. But these repair systems work at a finite rate. When radiation hits faster than the body can fix the damage, errors accumulate. Some cells die outright. Others survive with mutations that might trigger cancer years or decades later. The dice get loaded against you, one proton at a time. Commercial aviation is seriously disrupted. All polar routes are redirected to lower latitudes, even if it means significantly longer flight times. A transpolar flight from New York to Hong Kong might have to route south over Europe and Central Asia, adding hours. Passengers at cruising altitude during an S3 storm receive radiation doses equivalent to several chest X-rays. Pregnant women are advised against flying. High-frequency radio goes dark over large sections of Earth. Military communication networks that rely on HF radio lose connectivity. Amateur radio operators find entire frequency bands unusable. GPS accuracy degrades enough that precision applications become unreliable. Autonomous vehicles, precision farming equipment, surveying tools, all compromised. S3 storms can last several days. The sun is hurling protons at Earth in sustained bursts, and there's no shelter except what we've built. Underground facilities are fine. Sea level is mostly fine. But in orbit, at altitude, near the poles, you're exposed. And if you think several days of this is bad, imagine what happens when the proton flux climbs another 10 times higher, where the damage becomes permanent and the risks turn lethal. S4, proton flux, 10,000 particles per square centimeter per second per steradian, 10 times worse than S3. We're approaching the upper limits of what our current technology can handle. S4 storms are rare, about 3 times per solar cycle. When one hits, it's an event. Space agencies go into crisis mode. Satellite operators activate emergency protocols, airlines cancel flights, and anyone in space is in immediate danger. Satellites start failing outright. Electronics fry. Memory systems corrupt beyond recovery. Solar panels degrade so badly that some satellites can't generate enough power to function. Communication satellites go offline, creating dead zones in coverage. GPS constellations lose satellites, and with fewer satellites available, accuracy plummets and coverage becomes spotty. At this intensity, the physics of radiation damage shifts into overdrive. Protons aren't just flipping bits anymore, they're causing latch-up events where entire circuits become stuck in high current states, burning themselves out. Imagine a circuit board where a single proton strike creates a short circuit that draws so much current, it melts the traces. This is what's happening inside satellites during an S4 storm. The International Space Station's radiation alarms are screaming. Astronauts crowd into the most shielded module, often the Russian service module or areas surrounded by water and supply storage, because even those thin layers of matter help. They're receiving radiation doses that approach annual limits in a matter of hours. Long-term health risks, cancer, cataracts, become statistical certainties. NASA and other space agencies are calculating, how much longer can the crew stay up there? Do we need to evacuate? The decision to evacuate the ISS isn't taken lightly. It means abandoning billions of dollars of research, potentially losing experiments that have been running for months or years. It means the station will be unoccupied, vulnerable to systems failures with no one aboard to fix them. But when radiation levels hit S4, staying becomes unconscionable. The crew's lives and long-term health take priority over everything else. The evacuation procedure itself is dangerous. Soyuz and Dragon capsules must undock, maneuver away from the station, and execute a precise re-entry through the atmosphere, all while radiation levels remain elevated. The crew inside those capsules are still exposed, though less than they would be on the station. Every minute counts. Every decision could mean the difference between acceptable risk and unacceptable harm. Aviation is grounded over huge swaths of the planet. Not just polar routes, all high-latitude flights. Flying over Canada, Northern Europe, Russia becomes an unacceptable risk. The radiation dose for crew and passengers would exceed safety limits. Airlines lose millions in cancellations and reroutes. Power grids start feeling secondary effects. The same energetic protons that hit satellites also slam into Earth's magnetosphere and ionosphere, causing geomagnetic disturbances. These can induce currents in long-distance power transmission lines, causing transformers to overheat. It's not the direct radiation that threatens ground infrastructure. It's the cascading electromagnetic effects. Radio communication is nearly impossible across large regions. Emergency services that rely on HF radio for backup communication find themselves cut off. Military operations are severely hampered. GPS-dependent systems, everything from precision agriculture to missile guidance, lose reliability. And here's the terrifying part. S4 storms can last a week. 7 days of sustained bombardment by energetic protons, 7 days of satellites dying, flights grounded, astronauts huddled in makeshift shelters, and critical infrastructure degrading. By the time it ends, the damage is measured in billions of dollars and potentially in lives, astronauts exceeding safe radiation limits, passengers on high-latitude flights who insisted on traveling, people dependent on systems that stopped working. But S4 isn't at the top of the scale. There's one more level. And it's the kind of storm that doesn't just damage our technology, it tests whether our civilization can survive without it. S5. Proton flux, greater than 100,000 particles per square centimeter per second per steradian. This is the monster, the once-in-a-lifetime event that makes you question whether we were ready to become a spacefaring species at all. S5 storms are exceedingly rare, less than 1 per solar cycle on average. The last significant one occurred on August 4th, 1972, between Apollo 16 and Apollo 17. If it had hit while astronauts were on the moon, they would have received potentially lethal radiation doses. NASA got lucky. Timing saved lives. When an S5 storm strikes, satellites don't just malfunction. They die permanently. Electronics are fried by the sheer intensity of particle radiation. Solar panels are degraded to uselessness. Entire constellations go dark. GPS gone. Communication satellites gone. Weather satellites gone. We lose our eyes in space. The scale of destruction is unprecedented in the space age. Imagine watching hundreds of satellites go offline within hours. Not glitching, not rebooting, just dead. The control rooms at satellite operators around the world light up with critical failure alarms. Engineers stare at screens showing flat telemetry, no heartbeat, no response. Billions of dollars of hardware transformed into orbiting debris. The International Space Station becomes a death trap. Even in the most shielded areas, astronauts are receiving doses that guarantee long-term health effects and could cause acute radiation sickness. Evacuation is the only option, but if the storm comes on quickly, if the spacecraft isn't ready, if the crew can't get to a Soyuz or Dragon capsule in time, they're trapped. Waiting out the storm means accepting radiation exposure that could kill them years later through cancer. The terrifying reality of an S5 storm hitting the ISS is that the crew might not have time to prepare. These storms can arrive with as little as 15 minutes warning. Astronauts would have to abandon whatever they're doing, secure critical systems, grab essential supplies, and get into their spacecraft for evacuation. But Soyuz and Dragon capsules need time to undock safely, time they might not have. Imagine being told you have a quarter of an hour before invisible death arrives. You can't see it coming. You can't feel it until it's too late. You just know that somewhere between Earth and the Sun, a wall of high-energy protons is racing toward you at nearly the speed of light, and there's no bunker deep enough in the thin metal shell of the ISS to keep you safe. Aviation doesn't just ground polar flights. It grounds everything above certain latitudes for days. Huge chunks of international travel stop. Supply chains that depend on air freight collapse, perishable goods spoil, time-sensitive shipments miss deadlines. The economic impact spirals into the hundreds of billions. Power grids worldwide face geomagnetic storms induced by the same solar event that created the radiation storm. Transformers fail, blackouts cascade. Regions that depend on long-distance, high-voltage transmission could lose power for weeks or months while transformers are replaced, and there aren't enough spare transformers. We don't keep warehouses full of multi-ton, custom-built electrical equipment on standby. Radio communication is dead over vast regions. HF, VHF, even some UHF bands are unusable. Emergency services fall back to whatever local systems still work. Military forces lose over-the-horizon communication capabilities. Ships at sea can't call for help. Aircraft can't contact ground control. GPS-dependent systems, all of them fail. Autonomous vehicles stop. Precision agriculture equipment sits idle. Financial systems that rely on GPS for time synchronization start experiencing errors. Navigation becomes manual, chart and compass, for ships and aircraft that still remember how. The storm lasts days, possibly a week. Every day the damage accumulates. More satellites fail, more radiation exposure, more infrastructure degradation, and even when the proton flux finally drops, when the storm passes, we're left counting the cost. In the 1972 event, we were lucky. We had fewer satellites, less dependence on GPS. No astronauts in space at that moment. If an S5 storm hit today with our satellite-dependent infrastructure, with astronauts permanently stationed in orbit, with aviation systems relying on GPS, the cascading failures could cripple modern civilization for months. And here's what should keep you awake at night. We can't predict them with much accuracy. We see the solar flare that launches the protons. We know a storm is coming, but we typically have only 15 minutes to a few hours of warning. Not enough time to bring astronauts home. Not enough time to safely shut down critical infrastructure. Just enough time to send out alerts and hope.